Okay, so last time we discussed computability and uncomputability arising in connection with problems, common numerical operations on computable real functions. So we have seen several both positive and negative results, some of them debunking numerical folklore and others supporting making a rigorous foundation to numerical folklore. So the first example was about a derivative. The derivative of a computable C1 function may be uncomputable, but if we have a good C1 function, if the derivative of that function has a computable modulus of continuity, then the derivative is guaranteed to again be computable, and that in particular applies to computable C infinity function on a compact interval. Then we discussed computability and uncomputability as arising from the partial derivative, the partial differential equation, the wave equation. First, we again constructed a counterexample based on the Myhill's example from above and using kind of explicit formula for the solution. And then we saw why this is not a contradiction to the Church-Turing hypothesis, namely we basically used the wrong norm. We consider the supremum norm in the space of continuous function with evaluation, whereas mathematics knows from a theory of solutions of partial differential equations that the right norm on this space of solutions is actually an integrable space, let's say L2 integrable solutions, where there is no single point evaluation. And finally, we discussed the problem of computing a root of a computable real function, or the argmin, an argument where the function attains its minimum. The minimum is guaranteed to exist and is unique on compact domains, but it may be attained on many arguments, and our admittedly artificial counterexample shows that in general none of these arguments where the minimum or the root is attained need to be computable. And on the positive side, we've seen a computable version of the intermediate value theorem, namely under the hypothesis that the function under consideration has proper roots, namely a proper root is a root which is where on one side of the root the function is strictly negative and on the other side is strictly positive, so it does not just touch the x-axis, but it really crosses the x-axis. And this construction of Specker was based on a computable strengthening of the classical singular coverings. Classically, we know that every countable subset of reals must be a set of Lebesgue measure 0. It can be covered by open intervals of arbitrarily small total length, total measure. And there's a computable version of that, namely the countable set of computable real numbers can be covered by countably many computable intervals with computable endpoints that in total have a small total length, namely length less than 1/2, for example. Okay, and I'd like to remind you of some peculiarities of the positive parts of these results. Namely, when we proved, for example, that the derivative of any computable C infinity function is again computable, the algorithm would hard code and bound on the second derivative, because that gives rise to computable modulus of continuity. Second derivative being bounded means that the first derivative is Lipschitz continuous, and the Lipschitz constant depends basically on that bound, and it's no loss of generality to suppose that that bound is a natural number, and therefore is a finite information that can be hard-coded. but the proof did not reveal any idea of how to obtain such a natural number. We only showed that it exists and then proceeded to, in our proof, to hard code it. But how can it be found? And indeed, in general, it cannot. We only know it exists. Similarly, for the intermediate value theorem, the computable intermediate value theorem, the proof would consider two cases. One where there's a dyadic rational as a root, then we would hard code that dyadic rational into our algorithm computing a root. And the second case where the function under consideration does not have any dyadic rational as a root, then we would apply the bisection algorithm, and that would work well because bisection plus strictly positive or strictly negative only can happen. There's no third case as based on our hypothesis that the function has no dyadic rational root. And now we're going to want to make these observations and their common philosophy formal by considering two extensions of computing, namely multifunctions as opposed to ordinary single-valued functions, and discrete enrichment. And this is the topic of chapter E of section 2 about computability and real computability and uncomputability. So to remind you, we proved that any computable function must necessarily be continuous. And as I pointed out, this is sometimes considered a severe restriction as it excludes many common and simple example functions, for example, the sine function. And in the proof, it was essential that we're talking about a function, that everything is kind of deterministic. That was a crucial ingredient in our proof. Then we would kind of run the computation, and then we would restart the same computation and exploit that the computation would proceed in the same way. And that, of course, only is true if the computation is deterministic and if the problem to be solved is a function problem. So function problems are problems where there's an input and given an argument and there's an output, and that output depends uniquely on the input. That's a functionality property. Whenever x is equal to x prime, then y and y prime must be equal. So that's a common logical formalization of the function problem. Okay, but there are other kind of problems already in the discrete setting, computational problems, namely so-called search problems. For a search problem, there's an input, but there's a variety of possible answers, of possible outputs. That's a search problem, right? So, for example, in our root finding problem, that's actually more suitably formalized as a search problem, because we're happy to output any root of the given function in case the function has many roots. If the function has only one root, then that's a function problem. It's a unique root. If the function has no root, then the whole problem is undefined. But if the function has several roots, then intuitively we should be satisfied with any possible root, any possible among many possibles. And to formalize this idea mathematically, search problems with not necessarily unique answers, unique values, we're considering what is sometimes called a multifunction. So we use this symbol to denote a multifunction. An ordinary arrow says it's a single-valued function, and we abuse this symbol to denote a multifunction. And this symbol is to denote that it's a partial function. It's not necessarily defined on every possible small x in this set capital X, but only on some of them. So, and mathematically, what we call a multifunction can mathematically be considered just as a relation. Every function is a relation with this additional functionality axiom. If x is equal to x prime, then g of x and g of x prime must be equal. And we relax that condition and thus arrive at an ordinary relation. However, this mathematical conception of a relation is not does not really nicely capture the semantics we're assigning to this relation as a search problem. And that's even more true by another reasonable mathematical formalization of our search problem, maybe as a set function, where the argument is some x, as here, and the value is a set of possible y value. So P here means the power set. So a subset of all possible, some subset of capital Y of the codomain. That's a set of possible return values. And I will explain in a minute why this, although mathematically natural, is actually misleading. It's not wrong, but it's a misleading way of looking at search problems semantically. So such multifunctions are sometimes called non-extensional functions, but of course this is an oxymoron because extensionality is the defining axiom of functions. And in the discrete case, search problems, any computation of a search problem actually computes a selection, actually computes a single valued. If you have a deterministic algorithm and run that algorithm again, once on input x and once on input x prime, and both inputs agree, then deterministic algorithm basically means that the output will be the same, so that a computation of a search problem actually computes not a search problem but a function. But as we're going to see, when we leave the discrete realm, when we talk about computing with continuous and in particular with real arguments, then there are natural examples of multifunctions which are computable, but which do not have a computable single-valued selection. Okay, let me say that again. In the discrete setting, any computable multifunction, any computable search problem has, actually is computed as a single-valued function, a selection. But in the continuous realm of real multifunctions, we will see examples where the multifunction is computable, but has no computable single function as a restriction. And the basic prime example is the sine function, which is supposed to be, let's say, or Heaviside function, which is supposed to be 0 for arguments less than 0, and which is supposed to be 1 for arguments greater than 0. And of course, there's a jump here when the argument switches from negative to positive, then the value jumps, so that the sine function or the Heaviside function is discontinuous and therefore uncomputable. But what you see here is not the sine or the Heaviside function. You can see there's some overlap for arguments that are sufficiently close to 0, closer than epsilon, where epsilon is a parameter which we'll talk about in a minute. There are two possible answers, right? This is the essence of a search problem. So when the argument is sufficiently close to 0, then the sine multifunction you see here could report that the argument is negative, or could report that the argument is positive, although mathematically it is only one of the two. It is either negative or positive or 0. But here, for instance, this argument, this overlap means that both answers are acceptable, and that's the essence of a search problem. And this is important because this non-extensional, this multi-valued search problem is actually computable, whereas without the overlap, it is discontinuous and therefore not computable, as we proved previously. So that's an important point observation. By relaxing the functionality axiom, by allowing such an overlap, by making the problem non-extensional, the problem, such a discontinuous problem, may become computable. So we already saw why this case is not computable. So let me demonstrate and explain why this multifunction with overlap is computable. And to this end, recall our definition of what it means to compute a function. To compute a function means given approximations to the actual real argument, output approximation to the actual real value. And now the algorithm to computing this multifunction just looks at the approximation to the argument and checks whether the approximation and when the approximations become closer to 0 than epsilon. And if so, then it can output anything, right? Whereas if the approximation, current approximation is has magnitude greater than epsilon, then we can check whether the real argument, which is represented by this approximation, is positive or not. Because if the approximation is greater than epsilon, right, then that means that the actual real argument must be greater than 0. It's an epsilon approximation after all. And if the real argument is greater than 0, then we're safe to output this value plus 1. Whereas if the approximation is less than minus epsilon, then we're safe to output this for the value, because then the argument is guaranteed to be negative. Only when the approximation is close to 0 in this interval, then we can never be sure whether the argument is actually negative or positive or equal to 0. That was the essence of our proof that any computable function is continuous. But now this being a multifunction, this having an overlap, if the input approximation has magnitude less than epsilon, if we are not sure whether the actual real argument is positive or negative or equal to 0, then we can output anything, right? And that's a basic algorithm that allows us to compute this multifunction for any fixed epsilon, right? As long as there's some overlap, then we're good. If epsilon is 0, if the overlap is absent, then we're back to this uncomputability due to lack of continuity. So any finite overlap, but any finite overlap also destroys the functionality property. And observe that the algorithm I've just described indeed depends on how the argument x is presented. Namely, the algorithm looks at the approximation. And if the approximation is actually greater than epsilon, then the algorithm will proceed in one way. And if the approximation is between 0 and epsilon, then the algorithm will proceed in a different way. So the behavior and the output of the algorithm really depends on how the actual real number argument is presented at by which sequence of approximation it is presented. So it does not only depend on the value of the real argument, but also on how the real argument is presented. And this is exactly the violation of extensionality. Two coinciding real arguments given with different sequence of approximations can give rise to two different values, and that's a violation of the functionality axiom, which makes a difference between computability and uncomputability. So to summarize, a non-extensionality multifunctions are crucial already with a simple example of the sine or Heaviside function, allowing for non-extensionality, allowing for an overlap, turn this uncomputable discontinuous problem into a computable but multi-valued problem. So that is justification why we should formalize and study more closely such multifunctions. On this slide, purely from the mathematical side, and on the next slide, from the computational side, the definition and properties. Okay, here you see two other examples of multifunctions. So there's a dark gray function, multifunction and a light gray multifunction. And an important property of computable or continuous functions is that both of them are closed under restriction. Restriction meaning if we make smaller the domain of the function. So topologically, if we have a continuous function, then every restriction of that function is again continuous. And computationally, if we have a computable real function, then any restriction of that computable real function is again computable, namely by the very same algorithm. As you may recall, our notion of computing real function indeed refrain from specifying any, from imposing any behavior for arguments outside of the domain. So the restriction of that function can basically reuse the algorithm of the original function, and thus computable functions are closed under restriction. Now, when we proceed from functions to multifunctions, there are actually two concepts that capture the essence of a restriction. A restriction can be seen as making a computational problem easier, right? So restricting the function means we promise that the algorithm will not have to deal with arguments outside of the restricted, of the smaller domain. And this is what you see here for the light gray part, right? So the dark gray part is defined as return values, actually several, right, on this range here, whereas the light gray does not require anything to the algorithm to behave anything for arguments that belong to this interval. It can still output something, but it doesn't really matter because the light gray part is a kind of restriction, has a smaller domain. At the same time, the light gray part is also easier than the dark gray part in another respect, namely the light gray part has more possible admissible return values, like for instance here. So the dark gray part only considers these y values as possible answers, whereas the light gray part also considers these as possible return values. So in this sense, having a larger values, set values, larger codomain, if you like, also makes the computational problem easier. And we're going to call this also a restriction, although the terminology is a little bit misleading, I have to admit, because actually it's not smaller, but the graph becomes larger. However, the graph becomes kind of larger in y direction, whereas here the graph becomes smaller in x directions. And this is both are ways of making a computational search problem easier by making its graph smaller in x direction and larger in y direction, if you like. And both will be called a restriction. And this both restriction immediately, that's why we call it restriction, have the property that any computable multifunction, when restricting it in either or both ways, making the domain smaller, removing parts of the domain, and making the codomain larger, adding additional possible answers to the codomain, makes the we can reuse the same algorithm for computing that multifunction, and in particular, the computable multifunctions are closed under both and under combined notions of restriction. So, right. So one subtlety about this computing of multifunctions is we don't require all possible or admitted y values in the function return value to be actually provided by the algorithm. So an algorithm that only computes the dark gray part here, for example, is an algorithm that computes also the light gray part, because we don't require all admitted light gray values to even occur during the computation. So that's why this conception of a partial multifunction as a set function is philosophically misleading, because as a set function, the natural conception is that if we enlarge here the values in the codomain, the power domain, then that's going to be a different multifunction, but actually it's a particular one where we simply ignore and don't require some values to occur. So this is what I called restriction. For classically, restriction should be make a computational problem easier by reducing the domain, but here as a multifunction, also making the codomain larger, admitting more possible return values, also is considered a restriction and makes the problem also easier. Okay, and I've now frequently already referred to what it means to compute a multifunction, but I still owe you the formal definition and notion. So let me get to that. So, right, as I pointed out, we're not going to follow up on the conception that a multifunction is just a set-valued single function, because that is misleading because of our particular semantics of the domain, and also relation is kind of misleading. You have noticed that the x and y axis, the domain and codomain, play very different roles. So when restricting, it means to reduce the domain and or to increase the codomain. So this is a very non-symmetric notion of semantics of a multifunction as a search problem, whereas the conception as a relation is inherently a symmetric one, and therefore misleading. It's not incorrect, but it is misleading. So to remind you what it means to compute a real function, and here again we use the symbol to denote partial function. Here's for you to a reminder. So argument is a sequence of numerators of dyadic rational arguments and dyadic rational numbers that approximate the actual given real argument up to error 2 to the minus n, with a promise or provided that the real argument belongs to the domain, otherwise the behavior is arbitrary. And the output must be a similar sequence of dyadic rational approximations, more precisely integer numerators to approximations to the value y, where y is now here an abbreviation to the value of that function f of x. And as you see, this notion heavily depends on the object to be computed to be a function, single valued, a single value y equals f of x. And our relaxation replaces that with a multifunction and replaces thus y be equal to f of x is relaxed to y being a possible and admitted value of f of x, where f of x is now denotes, as you recall, the set of admissible return values, the set of admissible answers to the search problem instance x. Okay, so this is the definition of what it means to compute a multifunction, and I leave it to you to now formally confirm that indeed this relaxed, or sometimes also called fuzzy, sign test with overlap of positive size epsilon is computable in this sense by the algorithm that I have just described in the previous slide. Another example of a search problem which is computable as a multi-valued setting, but not computable in any single valued sense, is the Archimedian property of the reals. To remind you, Classically, mathematically, the real numbers have the following property that ties them kind of to the integers, namely to every real number there exists an integer which is dominates, which is greater to or equal to that real numbers. So it basically captures that the real numbers are unbounded, but in a certain logical setting. And as you see, this to every r there exists. This is what logicians call a pi2 statement logically. For every, that's a universal quantifier. There exists, that's an existential quantifier. That's the essence of pi2 statements. And we can try to scholemize that to ask whether there exists a function which receives as argument any real number and returns as value some integer z with this property. So this is what one could hope for or expect, a computable version of the Archimedean property where the function which receives a real number argument and returns integer value that dominates the real number. But there exists no such computable such function. Why not? Well, if we have a computable such function, let's suppose that for a proof by contradiction, then remember such a function would be continuous, right? A continuous function from a connected domain of real numbers to the totally disconnected domain of integers. And as you know from topology, any continuous function on a connected domain is again has a connected codomain, and the only connected subset of the integers are the singleton. So that means any computable and every continuous such function must necessarily be constant. And obviously, any constant such function cannot satisfy this property for not for all possible real number arguments, only for some of them, right? So that's a proof that exists no computable function capturing the Archimedean property of the reals. Function, emphasis on function. However, since we're talking about relaxing function to multifunction, indeed, there exists a computable multifunction with this property, where multifunction is now emphasized with replacing the single arrow with this double arrow here. And the proof again is following algorithm. So the algorithm receives as argument approximations in this sense to the actual given real number argument. And what the algorithm will do is look at the zeroth approximation where m is equal to 0, which is just an integer, right? So when m is equal to 0, then the denominator is 2 to the 0, which means it's basically absent. And so basically we get an integer approximation to the actual real number argument x. And now what our algorithm can do is add, let's say, 2 to that integer approximation and claim that this is indeed a bound dominates the actual real number argument, because, well, the real number argument can differ from the integer approximation by at most 2 to the minus 0, which is 1, and therefore the actual real number argument will be at most the integer approximation plus 1, and so we can actually output that integer approximation plus 1 or plus 2 if we want to be on the safe side. So that's an algorithm computing this multifunction, right? It looks not at the real argument, but it looks at the given approximation to that real argument to obtain an integer which dominates the given real argument. And again, let me emphasize that this algorithm really and the computation really output something that depends not only on the real argument, but that depends on the given approximation to the real argument. Namely, if we, let's say the real argument is 0, and we output approximation to 0, like 1, 1 over 2, 1 over 4, that are valid approximations to 0, right? They are approximations up to 2 to the minus 0, 2 to the minus 1, 2 to the minus 2. And in this case, so when the real argument is 0, but the approximations are kind of approximations from above, in this case, the algorithm we've just described would output 2, integer 2, which is valid, right? Yeah, it's a correct algorithm after all. Whereas if we run the same algorithm with the same real argument r equal to 0, but approximation from below, let's say approximation minus 1, minus 1 over 2, minus 1 over 4, these are also valid approximation to the same real number argument 0. In this case, the algorithm would output a different upper bound. So also a valid upper bound to 0, but a different one, which is tantamount to this algorithm really being non-extensional. The output integer produced by the algorithm I've described really depends not just on the real number argument, but on how the real number argument is presented by which kind of sequence of approximation it is given. And this is the kind of violation or relaxation of functionality that makes the difference between uncomputability and computability, between multifunction and function, in this example of the Archimedian property of the real numbers. And another more involved, but arguably equally natural computational problem is about the fundamental theorem of algebra. What is the fundamental theorem of algebra? As you know, a fundamental theorem of algebra says that every polynomial with, let's say, complex coefficients of degree d has precisely d roots in the complex plane. Precisely d roots when we also count multiplicities. And it's no loss of generality to restrict to monic polynomials, that is, polynomials where the leading coefficient, the coefficient to the highest argument power, is normalized to be 1, so that we can formalize the fundamental theorem of algebra as a computational problem given a monic polynomial of, let's say, degree d, monic, normalized. So, or rather, given the coefficients of a monic polynomial of degree d, that is a coefficient vector of d coefficients, because the leading coefficient, we can ignore that's 1, right? That's kind of implicit. So, given the coefficients a0 up to ad minus 1 to a monic polynomial, which you can see here, it's a polynomial of degree d, and it's monic because we have already made sure that the leading coefficient is 1 here and is not even part of the input anymore. So that's the input vector, a d-dimensional vector of complex number. Return the d roots according to the fundamental theorem of algebra, including multiplicity, right? So, and as you recall, that's basically the essence of the fundamental theorem of algebra, here formalized as a computational problem. Now it's again not hard to see that this problem is uncomputable as a function in the sense that return this d tuple in any certain prescribed order, right? Or let me say it differently, this problem is actually a search problem. Return some d tuple of roots, and if there maybe some of the roots are degenerate, if some of the d roots actually coincide, then we could kind of permute these roots. Or more generally, since the complex numbers do not have a linear order, we cannot impose any order in which this d tuple of roots is to be produced. Or even more generally, any permutation of a given d tuple of roots is again an admissible answer to the search problem mathematically. And this is naturally formalized as a multifunction. So input this d-tuple of coefficients, output any d-tuple of complex numbers, including multiplicities, that constitute all the roots. So any permutation will again be permitted. And Ernst Becker has proven that without such a relaxation, when imposing any order on the d-tuple of roots, the problem is uncomputable. But when making the problem multi-valued, which I'd like to keep emphasizing is really natural here to do, then the problem is computable. There exists an algorithm that receives as input approximation to the d-tuple of polynomial coefficients and returns approximations to some d-tuple of complex roots. Okay, so that was about mathematical formalization of multifunctions and their motivation when computing with continuous data, in particular when computing with real numbers, where there are many examples, as I keep pointing out. These are examples of problems, multifunctional search problems in the continuous realm, which are computable as multifunctions, but they have no single or functional computable version. When we impose that this is an actual function, then it becomes necessarily discontinuous and thus uncomputable. And same here for the computational version of the fundamental theorem of algebra according to Becker. So that's why multifunctions are so crucial and unavoidable when we talk about real computation and real computability. I mean, the other, right, and I have pointed out that this kind of relaxation makes, for example, the sine or the Heaviside function computable, allowing an overlap, making it a multifunction. So relaxing a computational problem from a functional to a search problem to a multifunction can make a previously uncomputable problem computable without, of course, sacrificing the practical applicability. For the Archimedian property, we are in general not really interested in a specific upper integer upper bound for the fundamental theorem of algebra. We are generally not interested in any specific order of the roots, and we cannot impose such an order. So that was our first categorical way of avoiding uncomputability due to discontinuity, relax the problem specification from a function problem to a search problem. And the second categorical or logical or set theoretical relaxation that allows to avoid uncomputability due to discontinuity is something called enrichment. That's terminology that comes from actually from constructive mathematics. In constructive mathematics, any existence proof, as you may recall, must be provided with an explicit construction. So indirect proofs or assuming non-existence and then raising a contradiction, that's actually prohibited in constructive mathematics. And there's a huge body of literature and logic about that's constructive mathematics. And in this literature, there's a very interesting work of Bruno Kreisel and Angus McIntyre, where they formalize the conception of enrichment. And we're kind of taking that conception from the realm of constructive mathematics to the computational setting, as I will describe here, as another independent means to avoid uncomputability due to discontinuity. So let me start with a very simple motivational example. This entire slide is about linear algebra, and you all know the rank function, which takes, let's say, d times d square matrix and returns the rank, which is a non-negative integer. It's a natural number. But this natural number depends discontinuously on the coefficients of the matrix. This is already true in the case d equals 1 of 1 times 1 matrix. If the 1 times 1 matrix is just one single real number, right? And if that entry of that number, if that entry is 0, then the matrix has rank 0. And if that entry is non-zero, then that 1 times 1 matrix has entry 1. So that's basically just the Heaviside function we've discussed on the previous slide, right? The rank of a 1 times 1 matrix is basically just the Heaviside function, which is discontinuous and therefore uncomputable. On the other hand, and that's what we call enrichment, if yeah, and this has important consequences. So, for example, the famous Gauss algorithm is not an admissible algorithm in the setting of real number computation, because Gauss algorithm, that's what is commonly used and maybe even mathematically, in pure mathematics, asserts, for instance, that the column rank is equal to the row rank, right? So the classical proof that a matrix column rank and row rank coincide is based on Gaussian elimination. And that's good enough for classical mathematical proof, but it's not a constructive proof, and it's not a computational algorithm, although it's called algorithm because it involves this pivoting phase in every round of the algorithm, right? So the algorithm proceeds in rounds, as you recall, over the, let's say, column of the matrix, putting the matrix into echelon standard form, row, column by column, and for each column looks for a non-zero pivot in that column. And looking for a non-zero pivot, that's exactly the test for inequality that we've seen previously to be uncomputable and as hard as a halting problem. So Gauss algorithm is not an algorithm in the setting of in our setting here because of the discontinuity, and also otherwise it would assert the rank function to be computable, which we know it's not because it's discontinuous. As a consequence, also other common problems in the algebra are actually uncomputable in our setting for trivial reasons. So for example, computing the dimension of a given matrix range, or even a basis of the range, computing the dimension of the kernel, computing a basis of the kernel. These are all uncomputable problems because the dimension of a kernel or a range, that's basically the rank or d minus the rank, right? Which is again discontinuous. And knowing a basis, that involves the cardinality of the basis, which is basically the dimension. So again, it's uncomputable. A lot of uncomputability in all in simple classical linear algebra. Eigenvectors, an eigenvector basis of a given, let's say, symmetric matrix, also uncomputable for the same reason. And this is annoying. Let me be pretty honest about that. I mean, a theory of computation, we have all these nice definitions, we have nice properties, closure under composition, but when having the consequence that all these natural problems are discontinuous and therefore uncomputable, this that's not a mathematical problem, that's a psychological. People don't like that, right? So, but there's a workaround, and that's what we're talking about here, and that's called enrichment. Right. Also observe that computing a basis here already is inherently a multivalued problem. In general, particularly if the matrix is degenerate, if it has repeated eigenvalues, then the basis is far from unique, and the specification of the problem should be such that any possible basis would be accepted as return value. Basis meaning a tuple of vectors, right? So how can we fix that using enrichment? And to fix that, let's recall our original problem. So given a matrix, means giving approximations, static rational approximations to the entries of that matrix. So d squared sequences of approximations here, and output a natural number, and that's of course uncomputable. On the other hand, if we enrich, that's the terminology, if we enrich the argument to the rank function with an additional natural number, namely the rank itself, then the rank function becomes trivially computable, right? Now, observe that this is a partial function because it requires that the second argument or actually is the rank of the matrix. And then the rank of the matrix is basically trivial to compute. Just pass on, read and pass on the second part of the argument which we have just added here. So far, so trivial. This kind of enrichment makes the rank computable, but trivially so. Less trivial is that also the other problems that we've discussed here as uncomputable all become computable with this very enrichment. So for example, the problem of computing a basis of the kernel, let's say an orthogonal, or let's say an orthonormal basis of the kernel. Naive specification input of the matrix, which is entries, d times d entries by sequence of static rational approximations, output some, right, multifunction, output some orthogonal or orthonormal basis. Let's say when the matrix has rank R, that means output R vectors, each vector having dimension d. That's, as I said, a discontinuous problem because even the number of vectors to be output R, that's the rank, and the rank is discontinuous, right? However, although it is a multi-valued problem, right? And in general, many possible orthonormal bases, even orthonormal, right? We can, for example, flip the signs of the individual vectors of that basis and still obtain many different orthonormal bases. So even under these conditions, it's still a multi-valued problem, but multi-valuedness in this case does not render the problem computable because there's still some inherent discontinuity about the rank. However, if we do the same thing here as we did here, namely enrich the argument, provide additional discrete argument which is promised to be the rank of the matrix, then it turns out, and this is not at all trivial anymore, that this problem becomes computable. Observe that indeed, now here, this is the same R as here. So there's now no discontinuity involved anymore, right? So the output is R tuple of d-dimensional vectors. And here, with this additional discrete argument added to the problem specification, it becomes computable. And the proof to that is basically look again at Gauss algorithm. Well, as you know, there are many variants of Gauss algorithm. It's used for echelon, bringing matrix into this canonical echelon form. It's used for computing an LU factorization, lower and upper factorization, triangular matrices factorization, more general LUP factorization, where this is a permutation matrix involved, since in general during Gaussian elimination we need to permute rows if we don't find a pivot classically, if we had test for equality. And but we will need here to prove that this problem becomes computable with this additional enrichment. We're going to use the LUPQ factorization, which is also sometimes called full pivoting, right? So P, recall, means we're permuting the rows. We're allowed to permute the rows, but of course the output should of the algorithm will include the permutation of the rows. That's the P permutation matrix. But with full pivoting, we also allow for permuting the columns of the matrix. And this Q is the permutation matrix which captures the column permutation. And classically, the specification of the LUPQ decomposition of Gaussian algorithm is full pivoting is input the matrix, output this lower triangle, upper triangular matrix, both with real coefficients, and permutation matrices P and Q, P row permutation, Q column permutation, and these permutation matrices are of course not real matrices but 0, 1 matrices with bit entries. And well, in general, this LUPQ decomposition is again not computable because it still involves pivot testing, right? It's still a Gaussian algorithm, but now comes the additional hypothesis. We're guaranteed that the matrix under consideration has rank R. So what we're going to do, we run this this classical Gaussian algorithm, but we only run R rounds. We're only going to look at the first R output columns, well, output columns because we're going to permute the input columns until we found R pairwise linear, until we found R linearly independent columns, until we've arrived at R linearly independent columns. And that's exactly where the guarantee here, the promise, comes into account. And this guarantee says they exist precisely R linearly independent columns, right? That's the definition of the rank. And so before we've reached the Rth column, then full pivoting is guaranteed to find a pivot, right? That's the whole point of having rank R. Full pivoting is guaranteed to find a non-zero element. And as I recall, non-zero test, that's at least semi-decidable. So we can run Gaussian algorithm with full pivoting, looking for non-zero pivots. And this hypothesis guarantees that this search will find a non-zero pivot indeed, and then proceed just with classical Gaussian elimination and look at the next column until we've found our columns, and then our algorithm will stop and terminate. It has found our linearly independent columns, and then it will, let's say, normalize them or also normalize them or whatever, thus arriving at the basis of the kernel, but it will not proceed to the R plus first round because in the R plus first round, we will not find, we already know that we will not find a pivot, and the algorithm will not be able to detect that. So we refrain from proceeding beyond the first R columns, beyond the R rounds. This is how and where this additional enrichment, this discrete information enters crucially into our rigorous algorithm for computing a LUPQ decomposition from which we can then find a kernel basis. Multi-valued, right? So L, U, P, and Q are in general not at all unique. So we're only looking for some LUPQ decomposition and for some kernel basis. Okay, to summarize so far, this additional integer, which is a discrete quantity that enriches the continuous real quantity, the entries of the real matrix A with an integer, that's what makes this problem computable, trivially so, just pass on. But that's also what makes this kernel basis problem computable and not at all trivial by careful re-examination of Gaussian elimination with its LUPQ decomposition. By the way, LUPQ decomposition was introduced and formalized by Alan Turing. It seems very rarely unknown. Alan Turing is actually the founder, can be considered as founder of computational linear algebra and has done a lot of stability. So for instance, the condition number of a matrix was defined by Alan Turing. Anyway, okay, moving on. So that's our first non-trivial example of a problem from linear algebra that is uncomputable as a continuous problem, but with this added enrichment, it becomes computable. And the same holds for the eigenbasis problem. So in the eigenbasis problem, we're given the entries of a matrix, D times D matrix, which here is promised to be symmetric. So we know from the spectral theorem, it has a complete basis of eigenvectors. And the problem is find such a basis. And we know that the cardinality of such a basis must be D vectors of dimension D each. And a common hypothesis in numerics is that the matrix be non-degenerate, that is, no double eigenvalues. And indeed, with this additional hypothesis, the problem becomes computable. And actually, there's a generalization to that. Namely, if we're given the promise that this given matrix has exactly delta distinct eigenvalues. So now delta does not count multiplicities. Or put differently, delta should be the cardinality of the set of eigenvalues. Set of eigenvalues means we don't count repeated eigenvalues repeatedly. Then this problem is actually computable. So, and here the enrichment is this delta, the cardinality of the spectrum of A, the number of distinct eigenvalues of the given matrix, which is an integer, which is a natural number somewhere between 1, in which corresponds to the case that all eigenvalues coincide, highly degenerate matrix, right? And delta can range up to D, the dimension of the matrix, which is the non-degenerate case where all eigenvalues are pairwise distinct, but all other intermediate values are also permitted, provided that they're given to the algorithm as additional discrete input. Discrete because it's a natural number, whereas the matrix entries are real numbers given by sequences of approximations. So this is our next example, non-trivial example of a problem in a linear algebra that originally is uncomputable, even as a multifunction, because you know the eigenvector basis is again not unique at all, even if we required it to be orthonormalized, but becomes computable when we provide additional discrete argument and integer delta with an appropriate semantics promised to be equal to the cardinality of the spectrum of the matrix. Then the problem becomes computable. And I leave it to you to figure that out. It's basically standard linear algebra, calculate the resultant and compute basis of the kernel of the result, basically. And that has very nice applications to computation. For instance, we can already tell from the declaration or specification of sometimes from the specification and declaration of a library function that this cannot rigorously compute the problem. So suppose, for instance, you're presented with a library that provides an algorithm or claims to provide an algorithm that diagonalizes a given matrix. So D times D matrix, D is the dimension. This is a two-dimensional array of the matrix entries. And this means that the output is again a two-dimensional array, D eigenvectors of dimension D each. And we can already see that this specification claims to suggests to solve a problem which is discontinuous and uncomputable. And we can already see that from the declaration, whereas enriching the declaration corresponding to the discrete enrichment, adding an additional integer argument, the number of distinct eigenvalues, which is denoted delta here, then there's a chance that this library function is actually fully correct, or put differently, we should try to write such library functions as addition to the IREM library. And actually, my PhD student, Simon Park, has written such an extended and rigorous implementation of the diagonalization problem. So that in this sense, real computability investigations can provide canonical declarations to numerical problems which naively would actually be uncomputable and therefore not rigorous declarations or even algorithms. And yeah, as I mentioned, enrichment is actually a term borrowed from logic, from constructive mathematics, from a paper from 1982 by Georg Kreisel and Angus MacIntyre that has appeared in the Brouwer Centenary Symposium. Brouwer, Luitzen Egbertus Brouwer, as you may know, was arguably the first rigorously constructive mathematician, which is kind of a anecdote. It's kind of funny because Brouwer is nowadays famous for his Brouwer fixed point theorem, but actually one has proven that the Brouwer fixed point theorem is not and cannot be proven constructively. But that's just a funny side remark. So Brouwer founded constructive mathematics. Telstra and Van Dalen, logicians from the Netherlands, edited this book to honor Brouwer, and Kreisel and MacIntyre in this book formalized the notion of enrichment in constructive mathematics, and we adopt that here to the setting of computability with continuous data. Okay, and this is going to be the last slide for today, where it provides more examples of how enrichment can turn uncomputable problems into computable problems, namely the problems that we've already discussed in the last chapter about computability and uncomputability of real functions. So as you recall, we had this counterexample of a computable C1 function whose derivative is not computable, and we proved that the derivative is again computable if and only if that derivative has a computable modulus of continuity. And if we now strengthen the hypothesis from computable C1 function to computable C2 function, then we had observed that the derivative is indeed again computable, because being a C2 function means that its second derivative on the compact unit interval is bounded, and this bound without loss of generality in an integer gives rise to a linear modulus of continuity, which is of course a computable one, but the question is, how can our algorithm find that bound on the second derivative? And our proof would just argue that such an integer bound exists and hard code it into the algorithm and avoid the question how this integer bound can be found. But now we can formalize that this is exactly enrichment to, let's say, automatic differentiation, enriching an algorithm that computes the derivative along with the original function when presented with the original function and some bound, natural number bound on the second derivative. And this is of course a discrete quantity, right? It's a natural number bound to the continuous quantity, the given computable C2 function as a continuous quantity. So this is a formalization or reconsideration of our previous example and counterexample from the perspective of discrete enrichment with such a natural number to be given to the algorithm that performs this automatic differentiation. Then we let us look again at our computable intermediate value theorem, where the statement says if we have a function which is negative on one end of the unit interval and positive on the other, and it's computable, then it has some computable root. That's a computable strengthening of the intermediate value theorem. But our proof would consider two different cases. The first case, if the function has no dyadic rational, then we can proceed with this standard bisection. Check the sign of the function at the midpoint of the interval. If the sign is negative, proceed to the left subinterval. If the sign is positive, proceed to the right subinterval, and thus perform an interval bisection of the actual of some root of this function. But this algorithm, this bisection, fails if the midpoint actually is a root initially or anywhere throughout the computation of that algorithm, or put differently, if the function, this bisection algorithm requires that the function under consideration does not have a dyadic rational root. It can have many other rational or irrational or transcendental roots, but no dyadic rational root. Otherwise, there could be a third case, in which case this sign determination could stall, could lead to an infinite computation. So that this algorithm actually is again, or our proof of this would involve some enrichment, namely even either the promise that the function under consideration has no dyadic rational root, or given such a dyadic rational root, which is again discrete information to be provided with original continuous function, namely dyadic rationals, or a discrete set, as you know. And the third and final example is about computing with analytic functions, or more precisely here with power series. Let's say we have a power series with a computable complex coefficient sequence, in the sense of, well, we talked about computable sequences. And let's say that this has a positive radius of convergence, R, for which exists this explicit formula, but this formula involves the limit superior, which is basically both supremum that can exceed computability according to Specker's sequence, and a limit which also can exceed computability according to Specker. So twice we can exceed the realm of computability, and indeed in general, even if a sequence, coefficient sequence is computable, then the convergence radius in general is not even computable with Oracle access to the halting problem. Now let's consider any smaller circle, strictly smaller radius, strictly smaller than the radius of convergence. Then by the very definition of the limit superior, there exists a bound B in natural numbers such that all coefficients grow at most at that fast, bounded in this term, and particularly they decay or don't grow faster than R to the M. And this knowing such a bound allows us to bound the tail of this Taylor series, which means we only need to consider the first finitely many terms in order to get an approximation up to error 2 to the minus n, which means we can actually compute the function induced by this power series, provided we know such an integer, any such integer. So this is a third example of how the continuous information, a computable coefficient sequence of complex number, needs and requires to be extended, provided with a discrete quantity, a natural number, to render the power series into a computable function. Okay, so that's all for today. Let's summarize. So today we've considered two conceptual methods of avoiding uncomputability due to discontinuity. The first is proceed from a function problem to a search problem, which we formalized as a multifunction. Multifunctions have this new and general notion of restriction in two ways, either making the domain smaller or making the codomain or the set of values, range of values, larger, or both. And then we talked about computability of multifunctions, and we've seen several problems that become computable only as multifunctions, such as the Archimedian property of the real numbers or the computable fundamental theorem of algebra. And our second concept that allows to avoid uncomputability due to discontinuity is discrete enrichment. In addition to the discrete argument, which could be, for instance, here a computable coefficient sequence or computable function, or here computable C2 function, or in the previous slide, entries to matrices in computational linear algebra. In addition to these continuous quantities, also provide some discrete quantity, which could, for instance, be some natural number bound, or natural number bound here, or a dyadic rational number numerator. And this is two main concepts from logic to render discontinuous and thus uncomputable problems computable. So that's all for today. Thanks for your attention, and see you next time. Bye.